What is the specific heat capacity of this type of glass? How much energy will the glass gain when it is heated from 41 to 71 Celsius? So for this topic, calorimetry, we're going to have two types of situations. One situation where we have one substance and the other situation where we have two substances. According to this word problem, how many substances are here? One or two? What is the first substance that the problem mentions? It says a 4 grams sample of glass. That is one of my substances, okay? Now let's see if we can find another substance. It says the 4 gram sample glass was heated from 1 to 41 and was found to have absorbed 32 joules of energy. What is the specific heat for this type of glass and how much energy will the same glass sample gain? How many substances are in this problem?
One.
One or two?
Two.
Okay, let's see. We have a sample of glass, okay, heated from 1 Celsius to 41 degrees Celsius. A temperature increase of 40 Celsius and was found to have absorbed 32 joules of energy as heat. Absorbs 32 joules of energy as heat. What are we talking about? Are we talking about the sample of glass or are we talking about another substance?
Sample of glass.
So in the entire problem, here we just have the sample of glass. So for this problem, we just have one substance. When you have one substance, you can directly use the specific heat capacity equation that we have over there, okay? This is for only one substance. Now, what do we know about the substance? We know that the substance is glass, is material glass, okay? And it has a mass of 4 grams. We also know that was heated from 1 Celsius to 41 degrees Celsius. Now, from this, we have a range of temperature. From range of temperature, we can get the changes in temperature. But in this case, the problem also gives you a temperature increase of 40. So when a problem mentions temperature increase or decrease, you're talking about delta T. So the problem directly is telling you that the delta T or the change in temperature here is 40 degrees. 40 degrees Celsius, okay? But we can get it, okay? We can get it from the equation too, okay? But still, we need to continue. It says, and was found to have absorbed 32 joules of energy as heat. To specify about energy, we need to write the letter Q. Q is equal to 32 joules. Now, another key word from this problem is the word absorbed, okay? By the word, I don't know why it doesn't show the right. Wait. Okay, absorbed. Because the problem says that it is absorbed, we're going to consider the symbol of this Q to be positive. When it says releases, means negative. Okay. Now, in part A, the problem asks you about the specific heat for this type of glass. The specific heat is, it is written like Cp, okay? C sub P, it is unknown. That's what you have to find in A. And then in part B tells you how much energy will the same glass sample gain. So because it is asking you about energy, energy is written as Q, okay? So it says how much energy will the same glass sample gain? So it is Q gain. If it's gain, it's also going to be positive, okay? But they are giving you a change in temperature from 41 degrees Celsius to 71 degrees Celsius. That's all the information that you can gather from the problem. So if you take a look to the equation, okay, you have that specific heat, which is C sub P, is equal to Q, or heat divided by the mass times that change in temperature. But if you are not sure that if the problem gives you the change in temperature, you can get it, okay? So you say delta T, you apply the formula that you know, that is final minus initial. The final temperature is 41 degrees Celsius. In part A, we're talking about part A, okay? So 41 degrees Celsius minus 1 degree Celsius. So this gives you a delta T of 40 degrees Celsius. Why are we getting delta T? Because we need it here in the formula, okay? The problem gave us the delta T, but sometimes you're not sure if the problem gave you the delta T, so you have to get it. In case that you have to get it, that's the simple process that you have to do. Now, the next step is focus on the question. It says in part A, it says that you need to find C sub P, or a specific heat capacity. So you apply the equation and you say Cp equals Q divided by the mass times delta T. Just plug in the givens. You have Q, that is energy, to be positive 32 joules, divided by the mass, which is 4 grams, and multiply times delta T that we got in the step before, that is 40 degrees Celsius. How much is this?
0.2.
Okay, this gives you 0.2. Now, what units are we going to write? Take a look. We have joules in the top, and we have grams and Celsius in the bottom. That means that Cp, or specific heat capacity, will be in joules over grams Celsius. Like that. That is the part A of the problem. In part B, it tells you that how much energy will the same glass sample gain? So you need to isolate for energy. Energy, or in this case, Q. So we're going to get the same equation and you will isolate Q. So the main equation is Cp equals Q divided by the mass delta T. You are isolating Q, okay? So Q is going to be equal to Cp times mass times delta T. That is the isolation that you should do. Specific heat times mass times delta T. But delta T in this case is different. Okay? It is from 41 to 71 degrees Celsius. So what is the delta T in the second part? Delta T for my part B is going to be equal to what? Final minus initial. So it is 71 minus 41.
30 will be 30.
This will be 30 degrees Celsius, okay? The delta T for this part is going to be 30 degrees Celsius. So now you can use it in your equation. And you say, Cp. What is Cp for this part? Cp depends on the substance. Specific heat capacity depends on the substance, okay? So what substance are we talking about? We're talking about a glass sample. From the glass sample, we already got the specific heat capacity. It's this one right here, okay? You just have to use it in the second part. So you say Cp for the glass sample is 0.2 joules over grams Celsius, okay? And you will multiply times the mass, that is 4 grams, and you will multiply times delta T, the one you got is 30 degrees Celsius. How much is this?
24.
24. And what units are we going to measure this? Take a look.
Joules.
It's joules, okay? Why? Because here in the procedure, you can cancel grams with grams. Estos son Celsius, esta cosa. Estos son Celsius, okay? Those Celsius, you're gonna cancel them with this Celsius over there. So the remaining unit will be just joules. And with this, you finish the problem. So as you can see, it's very simple. Just apply the formula when it is possible. Sometimes you have to get the delta T, the change in temperature, and sometimes it's going to be given. Just remember to have the same unit. Now, take a look. Here it was possible because you had grams and grams, but sometimes you're going to have kilograms and grams, so you have to do a conversion. Be aware of that. And the problem is over for now. Now, for this Q, the answer you got was positive or negative?
Positive.
So if it's positive means that the heat was absorbed, okay? That means when heating the glass sample, it absorbed heat. So when heating the glass sample, it absorbed heat. So does it make sense? Try to think about it. Does it make sense? Okay, when you heat your food in the oven or in the stove, what happens? Is the food cooler or hotter?
Hotter.
Hotter because it absorbs heat. So that's why I'm telling you. And for these problems, yes, you can apply the formulas, whatever, okay, but also it needs to make sense. So you are heating the glass sample. That means that the energy is being absorbed. That's what I want you to analyze. Very simple when you have one substance, but when it's a time to use two substances, we need to be using another procedure. So I really hope I can make it all. If not, I will continue in the next class. Okay? So for this problem, it says a hot, just minted copper coin is placed in 101 grams of water to cool. The water temperature changes by 8.39 degrees Celsius, and the temperature of the coin changes by 68 degrees Celsius. What is the mass of the coin? So for this problem, I want you to tell me how many substances are involved.
2.
We have two substances. We have the copper coin and we have water. So that is very important that you analyze. You have water and you have copper coin. So what I do when I have two substances, I separate the givens. Okay, I separate the givens according to the type of material, to the type of substance. So let's see. I will write here copper coin, and I will write here about the water. That's how I'm going to separate the givens. Okay. Let's picture the situation. So the copper coin, imagine this is the copper coin, okay, is placed inside water, a container with water. The reason you want the copper coin to be cool, okay, that is the reason. That is a situation that is happening here. So, in other words, the hot copper coin is placed in water the reason okay, the hot copper coin is placed in water to get cool. Okay, that is the reason. That's what I want you to understand in this problem. So that is important, okay? Hot copper coin is placed in water to get cool. Now, this sentence tells you what object is going to absorb and release energy. Remember what I told you in the beginning. I told you the substance with greater temperature will transfer energy to the one with less temperature. So here in this example, the hot copper coin is placed in water. How is the heat going to be transferred? Okay, from the wait, wait, the laptop is freezed. So let's analyze the situation. The copper coin is hot and is placed in water to get cool. So which one or what situation is occurring here? Is the coin transferring heat to the water, or is water transferring heat to the coin? What situation happens here, like A or like B?
A.
Like A, because the coin that is hot, okay, is transferring heat to the water. That is an analysis that you want not to avoid. Always do that, even if it takes a little longer, okay? So if the coin transfers energy to water, that means that the coin releases energy, and the water absorbs or gain energy. That is what we know as heat transfer, okay? So I'm going back to the exercise, and I say the copper coin is the substance that releases temperature, and the water is the one that gains temperature. That is important, and you will see why. So what do I know about the copper coin? Do I know the mass? Do I know the mass of the copper coin?
101 grams.
But that's not the copper coin, that's the water, okay? So it says the copper coin is placed in 101 grams of water to cool. Okay? So, no, the copper coin, I don't have the mass. Actually, I'm looking for the mass. It is written right here. I'm looking for the mass of the coin. Okay? So I'm looking for the mass of the coin, but I know the mass of water, that is 101 grams. Now, it tells me the water temperature changes by 8.39 degrees. In that case, because we're talking about water, I need to write the information in the water size. So it's not giving me an initial or final temperature. It's giving me temperature change. When temperature change is given, basically they are giving you delta T. Okay? And for water is 8.39 degrees Celsius. It is written there in the problem. Then it says the coin and the temperature of the coin changes by 68 degrees Celsius. So that means that the temperature change here for the copper coin is delta T equals to 68 degrees Celsius. Now, as you can see, the information that we have is just too little, okay? So we need to include more information in it. And this is where the table is very useful. Take a look at this table. It is called specific heat capacities. So in this table, you're gonna find specific heat capacities about substances. So because we're talking about copper coin and water, we're gonna focus on the two substances. One substance that is copper, okay, and the other that is water. So I'm going to focus on that, okay? So I have my copper and I have its specific heat, and I look for water and I have there its specific heat. So I'm going to write the information where it corresponds. So for copper, I have that the CP is 3.87 times 10 to the second power joules over kilogram Celsius. Notice that here I have kilograms, I don't have grams, okay? Which means that I have to do conversion from grams to kilograms. How many kilograms are 101 grams? How many kilograms are 101 grams? Just divide by 1,000. This is going to give you 0.101 kilograms. I don't need to show you the procedure, okay? Now, what is the CP of water? According to the table, the CP of water is 4,186, sorry, 4.186 times 10 to the third power joules over kilogram Celsius. Or you can just say 4,186 joules over kilogram Celsius. It's the same. Okay. Also here is the same as 387 joules over kilogram Celsius. One is with scientific notation, the other is not, but both mean the same. So from this, you go and apply the formula for calorimetry. When you have two substances, you're gonna need this formula. Q gain is equal to negative Q released. Another way to write it is Q absorbed is equal to negative Q lost. The two mean the same. Okay, the two mean the same. Now remember, what is the substance that absorbs energy or that gains energy? Gain or absorb? Which one gains or absorbs energy? It is written over there.
Water.
Q of water is going to be equal to the negative Q, the one who releases, that is the coin. Okay, and with this, you basically did half of the problem. Now, remember what we did here, that we isolate for Q, that is equal to specific heat, mass, and temperature. You're going to apply the same over here. So you say water is equal to CP of water times the mass of the water times delta T of the water. This is going to be equal to negative. I will put parentheses. This is a specific heat of the coin times the mass of the coin times delta T of the coin. So I'm going to be working with the equation like that. So what am I looking for? I am looking for the mass of the coin. After I have everything done, I will isolate for the mass of the coin. Okay? So just plug in the givens and isolate for it.